sine as being like this, which is the graph you get when you think about how the radius spins. Okay? Now we've taken it a step further. If this angle is called u, I'm going to call it u instead of theta. One sec, Eli. And then I'm going to make a bigger angle over here. Make this triangle, which has this reference angle, but this larger angle is called v. Okay? I can now talk about these two triangles, and they've got different properties because they're in different quadrants. And now we're taking it to another level, and this is the biggest jump. We're saying, what if you add these two angles?
It gives you the angle on the bottom left.
Yeah, what if you get an angle way down here, and this is u plus v? And now we're learning some magical rules about that angle that seem very random.
So isn't the only reason the cosine magically appears because you're kind of magically making a line that completes a triangle, right?
Yes, and that line is now down here. That line is now down here because we've added this angle and this angle.
So it's just basically it's just another side of the thing to complete the triangle.
Yeah.
Okay.
Yeah. It's except for wait, that's sine actually down here. That's completing the triangle. The cosine is this one over here, which I always think of as like the cosine. I think of it as almost being like a shadow. Like if I had a stick like that and I shined a light straight down, the sine would be this height, and the cosine would be like the length of this shadow underneath it. And that's one way to look at sine and cosine. The problem is we start spinning it and we start adding these angles like u and v. So that's why when we do cosine u plus v or sine 2 theta, these sines and cosines seem to magically appear. And I could do the proof of where they come from, but it's long and a lot of algebra and it's not very intuitive. So all I can say is we're spinning around a circle, and when I add u and v, certain things happen. When I double theta, certain other things happen. And we're using those to be clever. Hope that was helpful to some of you, actually. But
how did the ancient Romans know what the angle they were looking at was?
Yes.
They had all sorts of sundials and protractors, and the ancient Greeks, they did some guess and check, but the ancient Greeks had some brilliant measuring devices using a compass, not a compass like a magnet, but a compass, the one where you make a triangle and you make circles with a compass. Remember those?
Oh, yeah, I do.
With just a compass and a straight edge, not even a ruler. It didn't have marks. They could be like, this is square root of 2 long. It was fantastic. Yes, Nabil?
What ancient civilization has the biggest contribution to modern math?
Biggest.
Greatest.
I think René Descartes' Cartesian coordinate plane was probably the most important jump, but he couldn't have done it, obviously, without the Greeks, and specifically the Hindu-Arabic numbering system. The Arabs were probably helped him out the most.
The Phoenicians?
And now you're getting into subgroups of Greeks, and I don't know my ancient history that well. So, which specific Greeks? I don't know.
I thought you knew everything.
I'm working on it. Okay, real quick, may I finish this? And if it's about,
I was going to ask you how you find the degrees or whatever.
Okay, now how do you find the degrees? Good. Getting back to this problem. We know the sine of 4x equals 0. When does the sine equal 0? At what angles between 0 and 2 pi?
When does the sine equal 0?
Yeah, when does the sine equal 0?
At 0 pi.
0 when else?
360.
Sine 4x equals 0 when 4x equals 0.
And 180.
4x equals 360. And when 4x equals 180. Remember on the unit circle, those are all the places where y equals 0. So you can look at your chart.
Pi, pi over 2 and 2. Or no, pi, 0, pi, and 2 pi.
And then 360 divided by 4 is 90. 180 divided by 4 is 45.
So you just plug that back into the sine?
Well, now we're done. This is all we were asking for, is what is x.
But where did the sine go?
Okay. I asked myself a question. I said, when does the sine 4x equal 0? So this is the point where you go to your unit circle chart, and you say, when does the sine equal 0? Mm-hmm. And when the sine equals 0 is at 0, at 360, and at 180. Okay? So now, all you have to do is solve these equations,
and then
you're
you
done.
just take the 4 out.
Yeah,
Okay,
divide both sides by 4. And then we eliminate the 0 because it's not
Okay.
Because it's not
the one they want. Yep. Okay, so...
Wait, but 2 pi, they don't want 2 pi. Oh, but then you're dividing.
Yeah.
Okay.
Yep, okay, so that's how you would do number 18.
Can you do the tangent?
Wait, how do you get 4x equals 360 to 4x equals 180?
Here I just ask myself a question, when does sine equal 0?
But
And then I go to my chart.
so go the same thing, like 31680.
Yeah, it's like if I said, Eli, when does...
Stop it, you're making
If I said, when does the sine of theta equal square root of 2 over 2? Okay, you should go to your chart and you should tell me it's at 45 degrees and at 135 degrees, right?
Yeah.
So then I would say theta equals 45 and theta equals 135.
Okay.
The only difference is they've got a 4x instead of a theta, so after we do that we have to do a little more algebra.
Okay, and where the 90 and 45 come?
What's 360 divided by 4?
Oh, then it's 360 divided by 4.
90.
You got it.
Alright.
Alright, I'm glad you asked, Eli, because I was thinking I rushed that a little more than I should have. Okay. Now, you know what I'm going to do? I'm going to push things back a day and not start the new thing. And I'm going to say, with this in mind, start working now on...
Oh, can I do test questions with you now?
We may actually have time for that. Page 394. I'm going to say 1 through 17 odd. So on Monday when I check the homework, if you just have the answers written down, how much credit will I give you?
1%.
Oh, dare to dream. You guys are so cute
Well,
when
if
you
you
dream.
get it right.
Shut up.
Yeah, we're good.